We are now moving on to lesson 10 on friction. There are quite a few sections of the book that I think it would be good for you to read, and a bunch of good example problems for you. These are not all on friction, but these are the ones that we need to have done by about this time in this class. Friction is a force which, I say in quotes, is always in the opposite the direction of motion. That's not quite true, but it's close enough. Static friction is friction when things are not moving. If you have something just sitting there, then say you look at a table. You know, maybe you're at your desk or at a kitchen table or something like that. Look at that table. If you push on that table with an incredibly tiny amount of force, well, it's not going to move at all. But we know that F equals ma. So if I apply a force, shouldn't that also cause an acceleration? Static friction is the thing that prevents that from happening. If you push on something without a whole lot of force, static friction will actually overcome whatever force you're trying to apply and prevent the thing from moving. Static friction is sometimes difficult for people to comprehend. Every kind of pair of materials, so you know, if it's your kitchen table, then maybe it's the wood of your table on the tile of your floor or something like that. Those two materials together will have a certain resistance to motion, to moving. And so you have to apply a bunch of force to get things to start moving. If something isn't moving, it doesn't really want to start moving because of the static friction between it and whatever it is resting on. We can measure the amount of static friction that an object can possibly have. That force of static friction will always be less than or equal to a quantity called mu s. This funny looking letter right there is a mu, which we spell as mu. If we have to spell a letter, which sounds weird, we would spell it mu, and it looks like a cross between an M and a U, so that makes perfect sense that it would be like that. But that is a quantity that depends on what materials you're working with, and so I will give you mu. I will either give you mu in a problem, or I will ask you to solve for mu, depending on exactly what we need to be doing with it. And that is multiplied by the normal force there. That creates the force of static friction. I say here that force of static friction is a smart force, which is always enough to stop something from moving as long as it is less than a certain amount. Now, take your kitchen table, whatever, and take your pinky. Take your pinky and put it up to the side of the kitchen table and try to push the kitchen table across the ground with your pinky. You probably can't do it. You probably shouldn't try very hard. Don't try very hard on that. But imagine trying to push your kitchen table across the floor with your pinky. That's not going to work because the force that you can transmit through your pinky is just not enough to overcome the force of static friction. Maybe instead of your pinky, you can, I don't know, try multiple fingers or something like that. It's still probably not enough to overcome the force of static friction and move that object across the ground. To move something, to overcome static friction, you need to push on it with enough force that it actually begins moving. That's why I say that static friction is a smart force. If we think about it like this, you have the table and you're pushing on it with your pinky. Look at create a free body diagram for the table. The table experiences some forces. The table will experience gravity pulling down, normal force pushing up, and normally that's all that it would have. If no one's messing with the table, then it would just have gravity and normal, and that's it. But now you come in and you push on it with a tiny little force like that. Now it's got a force that way, pushing on it. If you're on a frictionless surface, if you've got frictionless tile in your house somehow, then even a tiny little force will cause a little bit of an acceleration. It won't be much acceleration because F equals ma, and if F is very small, then A will be very small as well. But even a tiny little force like that will cause the table to start moving. Obviously it doesn't in real life because of static friction. Static friction is a new force that will come into existence when you're trying to move something across a rough surface, and that new force will be directed the opposite direction. That static friction will be against the direction of your motion. So if you push like that on the table, then the ground, the tile, is going to push that way on the table to resist your desired motion like that. And if you push a little bit harder, then the force of static friction will increase to still cancel out the force from your pinky. Static friction is, as I said, a smart force. That's big air quotes because, you know, okay, the force isn't really smart, obviously. It's just whatever it needs to be to prevent motion. There's a maximum amount of static friction, though. Any set of materials and any objects will have some kind of static friction maximum to it. And that static friction maximum will be equal to mu s, which is that coefficient of static friction, times the normal force. One thing I want you to see in this is there is definitely a difference between the force of static friction and the coefficient of static friction. Those are not the same things. Those are related to each other, but the force of friction is not the coefficient of friction. This is another common mistake that I have seen on students' tests and such. They are related like this if you have a large normal force. If there's a large normal force acting on the object, like a heavy table, for example, has a large normal force, then the maximum amount of static friction is whatever that coefficient of friction is times the large normal force. Now, instead, if you take, you know, maybe your phone and you put it on the tile of your kitchen, then your phone probably has a lot lower mass than your table. I'm going to assume that your phone is lower mass than your table. And so lower mass, well, the normal force is usually equal to the force of gravity unless someone's pushing on something or, you know, piling something on the table or whatever. So the normal force is usually related to the force of gravity, which is mg. So the normal force on your phone is going to be a lot less than the normal force on your table. And so this maximum static friction is going to be lower with a lower mass object, meaning that it's easier to move. And that's what that less than or equal to sign gives us. It gives us the freedom to have a static friction, which could be zero. Zero is less than or equal to the coefficient of static friction times the normal force. You know, look at your table right now. If you're not pushing on it, then the amount of static friction on it is zero. And if there's any extra force going to the right or left, then the amount of static friction if there's any extra force like static friction acting on the table without anyone pushing on it, then the table would start moving because of friction. That doesn't make any sense at all. So static friction can be zero, and if no one is pushing on something, it's probably zero. If you're pushing on it a little bit, well, the static friction will be a little bit. It'll be whatever it needs to be against your motion, to counteract your motion. But Eventually, if you push on the object, the table, with enough force, it will eventually be enough that the table starts moving. That means that you have exceeded the maximum amount of static friction that that table can handle. And once that happens, the table starts moving. And when it starts moving, you don't have static friction anymore. Static literally means not moving. Static electricity is electricity that's just kind of stored in a doorknob. If you get like a static electric shock from touching a doorknob, that's because the electricity was just sitting there in the doorknob. The charges, in particular, were sitting there in the doorknob and not moving. Moving charges is just electric current, the stuff that comes out of the wall sockets and whatnot. So static means unmoving, and once you apply more force than the maximum amount of static friction, which is this, when you get to this maximum value, when you get to mu s times n, then anything beyond that, the object starts moving, and then you're in the realm of kinetic friction. When you're moving, you have to deal with this kinetic friction. There's a table in the book for a bunch of different mu's, and we'll actually be looking at that table shortly. And it's kind of interesting, I think. We can look from a more physics perspective, what is responsible for friction. You see here, the block here and the floor there, they're presented as being perfectly smooth, but nothing's really perfectly smooth in reality. There's always little bumps on it, especially if you look with a very good magnifying glass or a microscope or something, you'll see little bumps on the surfaces of objects. When you try to move one surface across another surface, if they're bumpy, then each surface has to overcome the bumps in the other surface in order to move past each other. So you're always having to move these bumps past each other. That takes some force to move the bumps past each other. There's also very subtle little intermolecular bonds that will happen. You bring any two molecules close enough together, not any two molecules, but many different kinds of molecules, when you bring them together, they'll actually start attracting each other, and they'll create very weak intermolecular bonds. I've always wondered why objects don't just like fall apart. Here's an example. This is made of atoms, right? Presumably. And the atoms make up molecules. And so, okay, this thing is made up of molecules. And I can understand why molecules stay together, because there's molecular bonds. The atoms form bonds with each other, which make a molecule together. But then, ever since I started learning about chemistry, I'm like, well, it's just a bunch of molecules. So why don't the molecules fall apart? Why don't all the molecules, like, they're not connected to each other. They should just, fall apart into molecular dust. Any object that you have should just fall apart into molecular dust, right? Well, obviously that doesn't happen. This doesn't fall apart to molecular dust because the molecules in this are attracted to the other molecules in this, and they create molecular bonds to stick to each other. Molecular bonds are not as strong, intermolecular bonds, the bonds between molecules, are not as strong as the bonds that create molecules. When atoms bond together, that is a very strong bond. When molecules bond together, that's a much weaker bond that they have with each other. And so, it takes fire, it takes heat, it takes chemical reactions to break apart molecules. But I don't want to break this apart, but you could snap this apart. You could overcome all those intermolecular bonds just with your physical strength without the need for chemicals or without heat or anything like that. So the bonds that make this up, the intermolecular bonds that hold the molecules together, is weaker than the bonds that hold the molecules themselves together, the atoms themselves into molecules. But, well, it's still a kind of force that allows things to stick together. And that actually happens when you take two objects and you try to move them across each other. You're actually creating little molecular bonds between the two surfaces as they move together. If you touch a table and move your hand across the table, then the molecules in your hand are actually making little bonds with the molecules in the table. They're very easy to break those bonds, but there's still a little bit of bonds, and so that's why you feel friction between things. That's one of the reasons that you feel friction between things. Here is that table that I promised you of coefficients of friction. A bunch of different materials, and notice that it's always something on something. One material will have a different coefficient of friction with another material. Material A will have one particular set of coefficient of friction with material B, and a different set with material C, and a different set with material D, and a different set with material A. So if you have steel on steel, the coefficient of static friction, that measurement of how hard it is to get something started moving, will be 0.74. If steel on steel, if two steel surfaces are already moving across each other, then you look at the kinetic friction and you see, oh, well, it's 0.57. It's actually a little bit easier to keep things moving across each other than it is to get them started moving. However, aluminum on steel is a little bit less, right there. Copper on steel is even less than that. And you can go down the list. Oh, copper on cast iron is really hard to start moving, but then kind of easy when you have it moving, kind of easy to keep it moving when you have it moving. Oh, okay. Glass on glass, well, you don't really want to, it's hard to get that started moving, but a little bit easier when you are moving. Look at this, Teflon on Teflon and Teflon on steel. Teflon is a material that they use to make non-stick kitchen utensils. If you want to fry something up in a skillet, for example, if you use a Teflon coated skillet, then you can hope that nothing is going to stick to that skillet. Teflon is a material that does not like creating intermolecular bonds with other materials. Teflon really hates making intermolecular bonds with things. And so you lose all the friction that you'd get from having intermolecular bonds. Teflon is also coated on things as a liquid or as a spray. And so that liquid spray, when it dries, it just becomes a smooth surface. So a Teflon surface does not like creating intermolecular bonds, and it's automatically very smooth because of how it's created. And so Teflon on Teflon or Teflon on steel, it doesn't matter. It's a smooth surface with very few divots and bumps, and it doesn't like making the intermolecular bonds. So that's why Teflon has such a low coefficient of static friction and kinetic friction. Rubber on concrete. This is like your tire on the road. Well, when everything is dry, you've got a good coefficient of static friction. You want static friction with the road. If your tire is slipping on the road, then you're not actually getting anywhere. You want your tire to have a good grip on the road. And a good grip means a good coefficient of static friction. If your tire is spinning, well, you know that's not really helping you out. So it's really good when everything is dry, but when rubber on wet concrete is tested, you get much lower coefficients of friction. So if you go out right now and start driving around, you've got a much worse coefficient of static friction on your tires when you're driving around on wet pavement, on wet concrete. And if you accidentally or for some reason apply too much force to your tires, say you're wanting to slow down, say that you're driving really fast and you see a stoplight and now you need to slow down, well, you need to rely on your tires having good grip with the ground in order to give you a backwards force to slow you down to a stop. And the coefficient of friction is, in a way, a measurement of that grip that you have with the ground. having a lower amount of grip means that you don't have as much force that you can use to slow yourself down. So that's why you need to be careful when it's raining, because you have lower grip on wet concrete than you do on dry concrete. We can look at these diagrams here. Now, this book puts a lot of stuff into the diagrams. It's somewhat overwhelming at times, but let's just take it one thing at a time. Let's start with this diagram right here in the upper left, diagram A. You've got the normal force up and you've got the weight down. You've just got a block and nobody's doing anything weird with it. So yeah, normal force up, weight down, it just sits there. Now, you start applying, in diagram B, you start applying a little bit of force. So you're not pulling very hard on this, you're just applying a little bit of force to the block. Well, this amount of force is not enough to get the block moving. And so that means that the block has to be having another force going in the opposite direction, and that's the static friction, the friction when things are not moving. A tiny little force this way gets counterbalanced by a tiny little force that way. If you pull on it harder, like this, well, you might have a somewhat more significant force pulling this way that can get counterbalanced by another force pointing the opposite way. The moment that you get to that limit, the force of static friction is equal to mu s times n. Remember, usually we just list the force of static friction as being less than or equal to mu s times n. Well, when you're equal to mu s times n, that means that you're just about to start sliding. You have to exceed it by 0.000000001 newtons, whatever, and that just gets taken out because of the 3 sig figs. And so we often just say, this is just the limit. When you're at that limit, you're just about to start moving. And then when you are moving, you're no longer experiencing static friction, you're experiencing kinetic friction. And so you use the other equation, mu k times n. You look up the different mu k. I will always give you the mu s's and mu k's that you need for a test, unless you are having to solve for a mu k or a mu s, in which case, well, you'll have to solve for it yourself. I do have an example for you. A 3-kilogram book sits on a table. The coefficient of static friction between the book and the table is 0.25. The coefficient of kinetic friction between the book and the table is 0.15. How much force is necessary to start the book moving from rest? Here's our setup. We've got a force applied that we're going to be using to start the book moving. We've got mu k, the coefficient of kinetic friction being 0.15, mu s, the coefficient of static friction being 0.25. And I give you the equations here. We want to just barely get it started moving. And so that means we're going to have to get the coefficient of static friction all the way up to its limit. Once you've taken the coefficient of static friction up to the limit, then the object will start moving. So that's our big clue here. Use Fs. We need to overcome static friction to start this thing moving. We can draw a free body diagram that just takes into account the y forces right there. Well, we've got normal pointing up, force of gravity pointing down. We can see that the normal is equal to the force of gravity, or normal is equal to mg. We can say, oh wait, I know mu s, it's 0.25. And so mu s times n, well, 0.25 times n, 0.25 times mg, and 0.25 times 3 times 9.8 for g, 3 times 9.8. I can figure out what that number is, 7.35. 0.25 times 3 times 9.8 is 7.35. And so this means, right here, that the maximum force that you can apply is 7.35 newtons. It's good to have a number to point to sometimes, but in this situation right there, if I pushed on the block with 0.1 newtons, then the force of static friction would be 0.1 newtons. It would counteract me in the exact same way. If I was pushing at 5 newtons, then the force of static friction would push back at me at 5 newtons. If I was pushing with 7.34 newtons, then the force of static friction would point back at me, would stop the block with 7.34 newtons. If I got to exactly that limit, that's the moment you'd actually start moving. This is kind of annoying to some people, that there's like limits and whatnot. So here's a way of thinking about it. To get this book to start moving, I need to exceed 7.35 newtons by 0.000000001 newtons. But who cares about that? We're just going to have 3 sig figs. So with 3 sig figs, that's 0. So if we just say 7.35 newtons and it's going to start moving at that point, that's good enough. And no one can be, accurate in the force that they're applying down to absurdly low limits. Really, this should have like an infinite number of zeros and then a 1, but mathematicians don't like me saying things like that. So I'm just going to say very tiny number. If we apply that force, then the block starts moving. Here is a variant on that problem that you'll find in the slides. Let's say that I'm pushing on the block with 7.35 newtons. Let's say that it started moving. Let's say that this is really part 2 of this problem. The block is now moving, and I'm still applying 7.35 newtons to it. We still have the same coefficients of friction. But now it's moving. We need to find the acceleration given that I'm applying 7.35 newtons to it. I can make a free body diagram. The normal force points up, the force of gravity points down, the force of friction points to the left, the force applied points to the right. I can see that the block or the book is not going to be diving into the table or flying off the table, so the net force in the y direction had better be 0. And so we only have to deal with the net force in x to find the acceleration in x. So I can say that F net x is equal to max. F net x, well, that's going to be all of our positive forces. This is x direction, so positive means pointing to the right. Negative forces are pointing to the left. So our positive force is Fa, so all of our positive forces, minus all of our negative forces. Force of friction there, F sub F is force of friction. That's equal to max. We can fill in what we know. We know that the force applied is 7.35 newtons. We know that the force of friction is going to be equal to mu times n. And so this is kinetic friction because this thing is now moving. We've got the kinetic friction. So we need the coefficient of kinetic friction times the normal force. That's equal to max. Keep plugging in what we know. 7.35 minus, we know mu k is 0.15. We then know that the normal is equal to the force of gravity, and the force of gravity is the mass times the acceleration due to gravity. Still equal to max. Keep plugging in what we know. We know that the mass is 3 kilograms. We know that that mass is 3 kilograms. We know that g is 9.8 meters per second squared. And you can solve for the acceleration in the x direction. Just to confirm, let's figure out, does the normal force actually equal mg? Well, if I take out all the other stuff that I don't need, I'm just looking at the y direction. I've got normal, and force of gravity is equal to mg, and the acceleration in y is 0. So yeah, normal does equal mg. I did get a question during that. Would the mass unit matter? In other words, is there a specific unit for the mass, or can we use the unit given to us in the question? Oh, that's a good question. We always need to convert to kilograms. I briefly mentioned this earlier in the semester, but we always need to convert to, here, I'll write it down here, kilograms, meters, and seconds. If we always convert to kilograms and meters and seconds, then we'll be doing good. And we will get these things right, because a Newton, 1 Newton is equal to 1 kilogram meters per second squared. So if we try to take an equation like F equals ma, and if we want the force to be in newtons, the mass has to be in kilograms and the acceleration has to be in meters per second squared. As long as we're using these units, our units like newtons will come out just fine. We'll see next week that we'll have units like joules for energy that will come out just fine. And so we always need to convert to these kinds of units. In the first part, we used coefficient of static friction being 0.25. We used friction, that coefficient, 0.25. In the second part, we used 0.15, right there. The reason for that is that in the first part, we said how much force applied is required to get it started moving. So it is not moving. If we're having to get it started moving, then that implies that it's not already moving. If it's not already moving, then we have to use the static friction. Static meaning unmoving, just like static electricity being electricity that's just sitting there in your doorknob waiting to attack you. And so static means unmoving. If we're trying to get it started moving, we have to overcome that static friction. On the other hand, in this, I didn't actually write it down on this piece of paper, but it's in the notes. I say that this book is already moving. And if it's already moving, we need to use the kinetic friction, K. Kinetic means moving. Kinetic energy is something that we'll learn about in not too long. So we can get that kinetic energy, or kinetic friction there, because this block is moving. So to summarize that, if something in your problem is not moving, at the beginning of the problem, at the moment the problem begins, if it's not moving, then you're going to deal with static friction. If it is moving, you're going to deal with kinetic friction. So being able to tell, is this object moving or stationary? Well, if it's stationary, static. If it's moving, it's kinetic.